Okay, let's get started. So I'm Renzo, or Laurentius Huber, and I'm a postdoc, a visiting fellow ERDA in the group of Peter Bandittini since almost 2.5 years now, I think. And the talk title that Peter suggested is High Fields and High Resolution Structural and Functional MRI, which is a pretty mighty title. As most of the titles in the summer course lecture series, also this title describes a whole research field. And Peter specifically asked this year all the speakers to focus on the limits of their respective fields. So since I cannot be an expert in every single sub-aspect of this huge field of high-resolution, high-field imaging, I will talk about the limits, and I will talk about the specific limits that I'm limited by. If you want to get deeper into it, there's a lot of material out there. For example, there's this International Society of Magnetic Resonance Imaging, the biggest MRM society out there, and they have these dedicated educational programs, usually the first 2 days of their annual meetings, and you can watch those educational talks online. Similarly, there are dedicated workshops about high-field imaging, for example, that one here from Heidelberg, where they also recorded the talks, and you can watch those. Also, I found that one of the major high-field scanner vendors, Siemens, they also organize these high-field user group meetings. And they also have talks, and they are freely available to watch online. And the nice thing of those talks is that they basically invite every group leader from every high-field site and ask them to describe to a very wide audience what they're working on. So this is very nice, these kind of talks, to get a big overview and the feeling of the field. If you want to have a more technical side of things, you can check out this YouTube channel that I'm trying to maintain, Layer fMRI, where I also upload talks that are a bit more technical. So high field and high resolution imaging is a huge field. As I said, there are almost 60 ultra-high field human scanners installed worldwide, almost everywhere. And there are new scanners being installed almost on a monthly basis now. So it's getting very, very popular. And the number of scanners is also reflected in the number of papers that are coming out. So down here, I focus only on those papers that use sub-millimeter high-resolution fMRI at high field strength. And you can see that it's really exploding, especially in the last few years, where you see this exponential increase. And it took a while. So from the first proof of principle papers, maybe in 2000, 2001, nobody could really trust the results and get a stable signal up to about 2012. And then it's just taking off. And depending on how you categorize neuroscience or method papers, it's actually the neuroscience papers that are taking over now, which is very exciting. And also, after 2017, just in this year, there are 3 special issues coming out in this Journal of Neuroscience, Neuroimaging. One neuroimage special issue about ultra-high fields, one about high spatio-temporal limits, and one particularly about the applications of high fields and high spatial resolutions, namely laminar MRI and fMRI. The reason why high fields are getting so popular is because the signal-to-noise ratio increases with higher fields, meaning that your signal quality for a given noise level is increasing. You heard the terms SNR already probably from Daniel Handwerker's talks a few weeks ago. And in this nice study, it's nicely summarized from Rolf Pohmann and colleagues, where they compared the SNR with very similar radio frequency hardware, a 32-channel head coil for 3 Tesla, 7 Tesla, and 9.4 Tesla. And they found that it's really increasing supralinearly, meaning that when you go from 3 Tesla to 7 Tesla, your signal-to-noise ratio is improved by more than a factor of 3. And you get another factor of 2 going to 9.4 Tesla. And you can use this high SNR for anything you like to improve your detection thresholds or to improve your resolution. And you can get images out of it, for example, looking like this image that I got from Falk Lüsenbrick from Magdeburg, where he did anatomical T1 imaging with 250 micron, which is pretty spectacular, especially on the top here, you can really nicely see the nice contrast of gray matter, white matter, and he has about 16 voxels across cortical depth. It's really an awesome data set. You can also download it online from this link. And like you can see new structures that you cannot easily see with lower resolutions. For example, every single like sulcus and gyri in the cerebellum, or also intracortical structures. For example, if I pause here, you might be able to see the stria of Gennari here in the calcarine sulcus. I've been told that I see things. If you are used to look at those kind of data for a long time, then you might agree with me that there is a kind of brighter stripe in the middle of the cortex here, the stria of Gennari. However, you also see in this kind of data set that it's not without limits. For example, down here you can see that there's this gradient. It looks pretty awesome at the top of the cortex, but at the bottom of the temporal lobes, it fades away. So there are challenges that I will talk about. It's not only the high anatomical resolution that's very beneficial at high fields, but it's also the high functional resolution, because there's a lot of information we can harvest at these sub-millimeter regimes. And this is just one example where for conventional resolutions of 3 millimeter for a finger movement task, like that one here, you only roughly know which brain areas are involved. For example, you know it's the sensory motor network. And going to higher and higher resolutions, you can start to separate those networks further. For example, to separate premotor from primary motor, or primary motor from primary sensory, which is just a millimeter away, to a secondary sensory, and so on. And pushing it even further to 0.75 millimeters, you start to see additional features like these striping patterns here that I'm very excited about, because I believe they refer to different cortical layers. And in this case of the motor cortex, I believe the bright pixels here, like 4 pixels maybe forming a line, refer to deeper layer 5B. And those are the layers that have these huge bed cells, basically the origin of the corticospinal tract. So if there's activity down there, we know it's output activity. Whereas, for example, the upper layers, they receive a lot of feedback input, for example, from the sensory cortex, from motor planning areas, and that's very valuable information for neuroscience. So it opens up a whole new level to look at brain systems and directional connectivity. And I will talk about that more details in next Friday in a week. Today, I will focus more on the challenges that we face going to these resolutions in the first place. And this is the list of challenges that I want to talk about. It's a very personal list of all the challenges that I'm dealing with. So let's jump right in. The first challenge of high-resolution imaging that I want to talk about is the sensitivity limitation of high resolutions. And to give you a more intuitive picture where this is coming from, I want to do this short back of the envelope estimation here. So you learned already from previous summer course lectures that in MRI, we are basically measuring magnetization of the proton spins. And when you have more magnetization, then you have a higher signal. Also meaning that when you divide your voxel into 2 smaller voxels, you have only half the spins available, half the magnetization, meaning that your signal-to-noise ratio is lower. So our signal-to-noise ratio is proportional to the amount of magnetization we have available, so that the volume, or aka the distance cubed. And this cubing law is quite unfortunate, because it means that we pay a huge price going to high resolution. So going from a conventional 3 millimeter fMRI voxel to an 0.75 millimeter fMRI voxel is only like a factor of 4 on the distance, but it's a huge reduction in volume. It's a factor of 64 in SNR hit. And that's really a big number to deal with. So there's no question we need to use advanced methodology and have some compromises here and there. And this is obviously also true for anatomical imaging, for example, going from a 1 millimeter to a 250 micron anatomical image, as I just showed you before. So one very efficient way of increasing the SNR is the field strength, going to higher and higher and higher field strength. So clinical field strengths of 3 Tesla usually exceed the detection threshold for about a 3 millimeter resolution for a movement task. 7 Tesla already gives you a whole new level of looking at these sub-millimeter scales where you might be able to identify these striping patterns, the layers. And 9.4 Tesla might even give you some extra performance. However, it also comes along with a lot of technical challenges that are kind of solved already for 7 Tesla. So I believe you can think of it with this car metaphor here, where 3 Tesla is the most cost-efficient way of doing things. It's out there for a while and it's robust. It works. And 7 Tesla However, to have the extra performance of the sub-millimeter resolutions, you need a more expensive car. And Porsche has been out there for long enough now that it basically just works. You push a button, you can buy it commercially, and in most of the cases, it's robust and understood. And this is not yet true for 9.4 Tesla in every aspect. You can break records, yes, but you need to have a whole team of engineers working on it, and every little component needs to work like perfectly in balance, and then you get 1 or 2 successful record-breaking experiments out of it, maybe. The next limitation that I want to talk about is the physiological noise. And you already heard about physiological noise from Daniel Handwerker. And this is particularly challenging at high fields because you always, I found it helpful to know where the source of noise is coming from. So Daniel Handwerker already showed you a few weeks ago this graph here, suggesting that the signal quality, the image SNR, is not linearly dependent on the signal stability. In fact, if you exceed a certain threshold and even improve the signal-to-noise ratio further and further, it doesn't really improve your stability anymore. And this comes from the fact that at this level, most of the noise in our data is not really coming from the noise of the machine. It's mostly coming from the noise of the brain. So if you have like cardiac pulsation or respiratory noise, this is kind of an upper limit in the TSNR. Also, in the very, very first summer course lecture, you saw this image from Peter Bandittini, suggesting that signal stability is also non-linearly dependent on the required time that you need to have to exceed your detection threshold for given effect sizes. And those two non-linear effects here can be quite unfortunate going to higher field strength. And I want to give you a more intuitive understanding of this by comparing 2 cases that I was fighting on in the last few years. So in one case here, I was trying to look at inhibitory signals, the negative bold. So when you have a finger tapping task like that, and then you have this huge positive signal in the contralateral side, and you have maybe this tiny inhibitory signal at the ipsilateral side. And this is so small, the effect size is only about 0.5%, that we are really, really contrast to noise limited. So we need about 30 minutes of good data to average to exceed the detection threshold and see it reliably. Similarly, in this experiment, where I looked at the other side of the cortex, and here I have a huge effect size. However, I'm still really limited by SNR because I want to have very, very high resolution. I want to identify these striping patterns here. And also in this case, I often need about 30 minutes of good data to average to get a stable result. So in both these cases, I'm similarly limited by SNR. But would you believe that in both cases, going to 7 Tesla helps a lot? Because it's actually quite different. In both cases, we need about 30 minutes of data, but we have different effect sizes, meaning that for the low resolution, a low effect size data set, we already start with relatively high SNR. And going then from 3 Tesla to 7 Tesla triples your signal quality. However, it improves your stability only by maybe 10% or so. And since you have a very low effect size, you are in this nonlinear regime here that improving your stability by 10% improves your acquisition time by maybe 2% or so. So you can reduce your acquisition time from 30 minutes to 29 minutes, which is not really a huge gain. And this is very different for high resolution, because there we start with a very low SNR, and then tripling your SNR also triples almost your TSNR. And so we are in a different nonlinear regime here, where going from 3 Tesla to 7 Tesla, tripling the SNR basically results in 5 times shorter acquisition time. So for high resolution, high fields help a lot. For low resolution, not so much. It depends on the case. The next big limit of high field, high resolution fMRI that I want to talk about is the complexity. And this limitation is not really a very scientific limitation, but it's very important nonetheless. And I believe this comes from the fact that fMRI is a big field already. So it has been developed like 20, 30 years ago. And structural MRI is even older than that, meaning that there are a lot of people, clever people, optimizing methods, building on more complex methods, making them not even more better, and so on. that it grew into this huge monster that almost nobody completely understands anymore. So in the early days, every person had to have a good spectrum of understanding every component of MRI scanning. For example, there's the hardware, the sequence development, then you adjust your contrast, you need to understand how to optimize your protocol before you can do your experiment and analyze the result and interpret them. And in the early days, people could change the sequence, put the person in the scanner, and look at the result in the evening. So they have a very efficient feedback loop and can start on the next day to know what needs to be improved and so on. And since it's so complicated nowadays, every little component here has its own research field, their own journals, their own conferences, that this kind of feedback loop becomes very inefficient. In fact, a lot of people doing experiments don't even know the person who set up the protocol. So for example, if I develop a sequence today, I need to wait maybe 4 years before the neuroscience person publishes their results, so I know why they're not happy with it and then what I need to change with it. And that's obviously more inefficient than doing it in one day. And this is particularly challenging at high fields and high resolution because you cannot simply assume that you change one single parameter here, like change the hardware from 3 Tesla to 7 Tesla, or change the resolution from 1 millimeter to half the millimeter and assume that all the rest just works. As soon as you are working in this new field, you need to basically reinvent all of these different steps, and they are complicated. So it's not only those 3 parameters here, there are actually more than 300 that you can adjust at the scanner. There are more than another 1,000 below the hood, and every single one of them is important. And less people have the willingness to spend years of training to understand the interdependencies of those and then figure out how to best optimize them. It's not a big problem for standard stuff where clever people have optimized this already, but as soon as you want to change something, then everything blows up sometimes. And the next big limitation of high-resolution fMRI that I want to talk about are the inhomogeneities. And I previously already talked about this with Falk-Lusenbrick's data. This is another data set where I scanned the same person at 7 Tesla and 3 Tesla with a 10-minute MP2 rate protocol, a sequence that is actually supposed to be quite insensitive to B1 plus inhomogeneities already. And you can see how different they look at 7 Tesla and 3 Tesla. So I think you can see up here that 3 Tesla is more noisy, 7 Tesla is higher resolution. However, 7 Tesla really dies, the signal dies down here. It looks awesome at the top of the brain, but as you go to the bottom of the temporal lobes, the signal becomes very weak, and also the bottom of the cerebellum is often gone, not even talking about the base of the brain here. So it really depends on which area you're interested in, on how much you benefit from these high fields. And one reason where these inhomogeneities are coming from is that with higher and higher field strength, we are working with higher and higher radio frequency waves, meaning that the wavelength becomes shorter and shorter. And at 7 Tesla or 9.4 Tesla, we are actually approaching the centimeter regime, meaning that there are these traveling wave patterns in a sense that there are waves going through the brain that can interfere constructively and destructively. And then if you don't do anything about it, for no PTX in this recent study at 9.4 Tesla that I did in Maastricht with Ben Poser, you can see that there's a factor of 20 or so in signal differences and in B1 plus differences within a few centimeters. And you can account for this partly by using a method called parallel transmit, PTX, where there are multiple transmit radio frequency antennas, like these coils around here, and then you can basically shift around the magnitude and the phase of your radio frequency pulses to manipulate the position of these destructive interference patterns. For example, in this case, we wanted to do we wanted to have a good inversion pulse for blood volume imaging and down at the circle of Willis, so we kind of shifted away the constructive and destructive interference patterns to have a good efficiency down here. Then for the readout and the excitation pulses, we were interested in the motor cortex, so then you can shift around the field to be focused more here. And one big challenge in this whole research field is the safety supervision. So since we are approaching the centimeter regime, we are basically approaching the microwave regime. And always when you have magnetic field changes, you can have hotspots of electric field changes, and you really don't want to heat up your tissue. Or if you do, then you want to know how much you heat up the tissue so you are sure that you're below the safety limits. So safety and SAR simulation is a big issue here. Another big challenge that I want to talk about are T2 star blurring effects, which really make my life hard, especially in combination with partial Fourier imaging. And this is particularly challenging at high resolutions and at high field strength. Like at high field strength, we have a shorter T2 star, meaning that the signal decays faster. And at high resolutions, it takes longer to acquire one EPI slice, meaning that more of the signal actually decays away. So in conventional 2D EPI, you would start with a lot of signal, and until you get to the last k-space lines, most of the signal is gone already. And this obviously looks very different depending on your trajectory. So the red case here refers to a conventional gradient out-center-out trajectory without partial Fourier imaging. And the blue case refers to something like a center-out, like with heavy partial Fourier imaging or spiral center-out or spin-echo EPI. And since every point in k-space refers to a different spatial frequency weight, the resulting blurring obviously looks very different for those two cases. And the math to describe this blurring has been described for quite a while now, often using this concept of the magnitude point spread function, where you assume that you have a linear imaging system and you can describe the blurriness of the final image by putting a point source through your imaging system and then convolve it with your object. I, however, have my issues with that because I believe we are mostly not using MRI as a linear imaging system. We usually are interested in the magnitude of the image, which comes from this nonlinear equation. And for those two trajectories, this math would say that the magnitude point spread function of the center-out spin echo acquisition in blue would be sharper, has a shorter full width half maximum. However, since we are non-linear here, as soon as you have a asymmetric k-space weighting, you also have this imaginary part in the complex point spread function, meaning that it can happen that the signal leakage from one voxel to its neighbor can be negative. So there's negative leakage and destructive interference patterns. So when we look at a more realistic case of a point source not on a zero background, but on a point source on a finite background, you can have these negative side lobes, which make the image actually sharper. And I would like to show you an example here of acquiring an EPI with a very long readout of an out-center-out trajectory and center-out half k-space trajectory. And you might be able to see that out-center-out is much, much crisper. You can really nicely see the dark layer 4 here, which has a lot of iron, clearer compared to the half k-space acquisition, even though the point spread function would suggest the other one should be sharper. And this is obviously also very helpful for fMRI, where, for example, we wanted to see this layer 4 in the primary sensory cortex or layer 5B in the motor cortex, which is only visible for the full k-space acquisition and is completely blurred away for the half k-space acquisition. So I take home from this that we really should consider doing partial Fourier. It can result in horrible blurring. And I also take home from this that we shouldn't be too much afraid of using long echo times because the resulting blurring is actually not that bad. We shouldn't overinterpret these magnitude point spread function. They're not so meaningful in most of the cases. The next limitation that I want to talk about are problems of off-resonances. And off-resonances are a curse and a blessing at high fields. So as soon as you're interested in susceptibility contrasts, like bold, for example, you get that the off-resonances are directly scaled with the field strength. So independent of the SNR increase, you even get more contrast at high field strength. However, there are also these unwanted susceptibility effects, for example, off-resonance effects in EPI or in ghosting and artifacts. And at high fields, we have this problem that we are usually approaching a regime where we are limited by the gradient speed, in the sense that usually an EPI image is acquired by going back and forth and back and forth and back and forth. So we kind of use the gradient in a resonant system. And for most of the gradients that are used at 7 Teslas, they have these acoustic resonances, in the sense that at certain frequencies and switching rates here, a lot of energy that you put into the gradient kind of builds up. It really starts to shake a lot. It becomes super loud and noisy, and you have eddy currents and motion, and the artifacts look horrible. And this is kind of doable at low resolution, because you can just shift away from your respective acoustic resonances. At high resolutions, we are much more sensitive to those, partly also because of the different gradient pulse forms. So at low resolution, we usually switch on the gradients, keep them on, acquire one k-space line, switch them in the other direction, keep them on, acquire the next k-space line, and back and forth and back and forth. At high resolution, however, because we use these bulky, huge body gradients, we are much more limited by the speed of the gradients compared to the magnitude, in the sense that the gradient pulse looks like the sawtooth pattern. And for this kind of pattern, any delay of k-space lines or even k-space lines cannot be simply corrected with a phase delay, because every point in k-space refers to a different gradient magnitude and therefore has a different phase offset. And I want to make this clearer by showing you a bunch of images with different bandwidth, starting from 960 hertz per pixel up to 1900 or almost 2000 hertz per pixel. And you can see that in the images, they often look fine. You often see the ghosts stronger in the TSNR images. And especially the higher bandwidth you use, the more ghosting you have. Especially right here, where the ghosting is almost as big as the signal itself. And you can see that it's not only the acoustic resonances, but it's the combination of the acoustic resonances with the ramp sampling, in the sense that this image and this image actually have the same switching rates of 0.92 milliseconds, but the ghosting level looks much, much better here, because here we can kind of account for it by adjusting odd and even k-space lines. And sometimes even more important than the switching rates of the actual data acquisition is the switching rates and inconsistencies of the calibration data. And at high resolutions, you're almost always forced to use acceleration with CRUPA. And for very unfortunate reasons, the conventional way of acquiring CRUPA calibration data is to first acquire all the odd k-space lines, and then in the next TR, acquire all the missing even k-space lines. Meaning that any tiny part of inconsistencies between the different TRs, for example, due to the fact that you are in different cycles of or different phases of your respiratory cycle or cardiac cycle, results in noise amplification. For example, you can see that there's a lot of noise, like maybe put into other places outside the brain. And there has been a lot of advancements about this in the recent years. For example, using different ordering of the reference data acquisition. For example, using a flash approach where the k-space lines are acquired in a more consecutive fashion. And you can see that this improves the image quality quite a bit. And it's not only important on how you acquire those reference data, but also how you use them in your reconstruction. For example, it matters what kernel size you use. It matters what kind of regularization you use. And actually everything matters. It matters what kind of flip angle you use, number of reference lines, everything. And I found it kind of weird why the reconstruction part of MRI method development does not really get the attention like the sequences do. For example, if you're interested in high-resolution fMRI with a surface coil at 7 Tesla, it's completely obvious that you use a different sequence as if you are interested in body imaging at 3 Tesla to look at kidneys or something. Why not? Yeah. But the way the system is set up is that the CRUPA reconstruction is completely identical for those two cases, meaning that in our 7T system, the default values of CRUPA reconstruction can be really improved for your specific case of, for example, high-resolution fMRI. Without much limits, only that you lose a bit of flexibility, that you cannot do kidney imaging with the same protocol, maybe. And this is particularly referring to the regularization here, where the default is pretty noisy. Improving it to 1000, this high parameter, really improves your signal. However, you also need to know that you can over-regularize it, for example, with 100,000 Ks. Maybe the take-home message here is that it makes a lot of sense to play around with those parameters because you can gain a lot. Another challenge of high-resolution, high-field imaging is that we are not really sure which kind of readout to use. And also in this direction, there have been a lot of advancements in the recent years. And I guess a lot of you heard already about this multi-band imaging, or SMS, simultaneous multi-slice, which is very helpful for high-resolution imaging because high-resolution imaging takes a lot of time. It's less efficient. It takes time to acquire all these huge amount of slices. So using simultaneous multi-slice can improve your efficiency by acquiring multiple slices at the same time, and then you acquire them in a consecutive fashion until you have the whole coverage that you're interested in. However, pretty much at the same time when SMS and multiband was introduced to fMRI, there was also this other method introduced to fMRI, 3D EPI. And in 3D EPI, you're using a different approach in the sense that you acquire this whole volume over and over again and just vary the different spatial frequency weights until you have the same resolution in both cases. And the difference in both cases, you can actually do the same kind of acceleration. So in SMS, you have in-plane Krapper acceleration and through-plane multiband acceleration. In 3D EPI, you can do the same acceleration in K-space. So you just do Krapper acceleration in both directions. And those two methods have been, they do have a different spectrum of sensitivity across different voxel sizes. So for very, very big voxels in the physiological noise-dominated regime of 3 mm fMRI, you can see that the 2D SMS really outperforms 3D EPI. And this is due to the fact that in the physiological noise-dominated regime, it helps a lot to have this snapshot-like acquisition of 2D EPI that kind of freezes physiological noise compared to the longer readout in K-space of 3D EPI. In the thermal noise-dominated regime of sub-millimeter voxels, however, at high resolutions, the 3D EPI really outperforms the 2D EPI. And you can better see these striping patterns that I'm interested in, these layers. So that's, I think, the method to go at very, very high resolutions. The field of high-resolution imaging is not only limited by the acquisition side. In fact, there's also people are also limited by the post-processing and the analysis. And to motivate this, I would like to show you some results of a study group survey that we did recently. So the International Society of Magnetic Resonance in Medicine has this specific study group on fMRI. And they asked all their study group members what they are mostly limited by in high-resolution imaging. And we asked about sensitivity, localization specificity, image distortions, registration quality, segmentation quality, and head motion. And you can see that in most of those factors, people feel differently limited by those, from 0, not limited, to 5, very limited. And to my huge surprise, people don't really seem super limited by sensitivity. It's actually the least limiting factor we asked, because they are much, much more limited by even other factors, for example, the post-processing. And registration quality seems to be the most limiting factor, but image distortions are also quite a challenge. And the fact that people are most limited by the post-processing is also visible in the answers to the question, which direction should the future efforts go to? Where most of the people think that we should invest more time in developing robust, streamlined analyses that work. Only half of the people think that we should actually investigate more and invest more time in better sequences, better hardware, more specific contrast, or better understanding the contrasts that we have. So let's talk about these limits. Let's talk about segmentation, for example. And the data set, in my opinion, that has by far the best segmentation out there compared to any other study is the data set from Kendrick Kay that he describes in this recent bioRxiv paper. And he provides these movies where he's flipping back and forth, like anatomical imaging, functional imaging overlaid with the different segmentation, like the surfaces, the borderlines between CSF and gray matter and gray matter and white matter. And when you zoom in a bit, you see it looks pretty spectacular mostly. However, if you're interested in sub-millimeter accuracy, then it can become problematic. And in fact, we are interested in sub-millimeter accuracy because that's the reason we acquired those small voxels in the first place. And then you can see it's never really perfect. They are always like here, the turquoise line should be shifted maybe two voxels to the left. Here it should be shifted 2 voxels to the right. They're missing some dark spots over here and so on. So as soon as you unfold the brain, then you see these dark stripes. So here Kendrick goes through the different cortical surfaces and sees all these dark stripes that he mostly interprets as veins. I believe that there are also these kind of circular patterns visible that I would interpret as registration problems too. So aside of Kendrick, I think almost all the high-resolution sub-millimeter fMRI papers out there require a lot of manual editing. So a lot of manual segmentation because it never really works perfectly at that level. And in my experience, it's particularly challenging in highly myelinated areas, for example, in the motor cortex or the primary visual cortex. So for example, in the motor cortex, we would expect that the cortical thickness is in the range of 4 millimeters. So for 0.75 millimeter, I would expect it here to have a distance of the red curve to the blue curve at least of 6 voxels. And you can see there is no clear borderline between gray matter and white matter. So I think it's not really a free surfer problem. It's just like an accuracy problem of having these high resolutions and having a lot of variability across different brain areas. For example, also on that side of the cortex where very often when 2 sides of gray matter touch each other in the sulcus, I often see these like unconnected areas. It never really works perfectly. And it's not only, I think, our problem, a lot of other people are also limited by that with these unconnected islands, for example. The next limitation that I want to talk about in the post-processing is motion. And it's obvious that when you have high resolution, you are more limited by motion. And everybody does retrospective motion correction, of course, but even this is not without limits. And Jonathan Polimeni pointed out that any kind of spatial resampling always reduces your effective resolution. So as soon as you have signal of 1 voxel that needs to be interpolated to a different voxel grid, that the signal of that 1 voxel is now distributed across the signal of 2 voxels. So you can basically, this can result in double the full width half maximum of your effective resolution after the motion correction or after any kind of spatial resampling, for example, distortion correction, registration to anatomy, and so on. And in this case, I found it very helpful to work on the interpolation and use optimized interpolation methods. For example, I think you can see here that the linear interpolation looks much, much smoother compared to a higher order spline interpolation. And another thing that I'm really worried in high-resolution motion is that most of the motion that we are limited by is actually not real head motion. It more refers to field motion because we are supposed to use these very low bandwidth with this big grading coil. So here, this is an example I acquired together with Daniel Handwerker with respiration, breathing manipulation, paced breathing, and you can see that most of the motion is actually motion in the phase encoding direction from the thorax moving, so your field is changing and therefore it looks like the brain is moving, even though it might not be actually moving. And at some high resolutions, obviously, the brain stops being a rigid body anymore. So for example, I found it very helpful to really optimize your motion estimation parameters in your area of interest. So in this case, I optimized my motion estimation parameters in the brain. So you can see that the brain is super still now, but the rest, like the skull and the skin, move quite a bit. And if I wouldn't do so, then my motion estimates would also include the skin and basically sacrifice the stability within the brain because the skull is moving differently. The last problem that I want to talk about are limits with respect to distortions. And the distortions at these high resolutions and high fields can be quite challenging. And this is just one example where I'm flipping back and forth a T1 weighted scan of a so-called anatomical scan and the same contrast in EPI. And you can see that the motion is often in the range of like the cortical thickness, meaning that when you are interested in like these subcortical signal distributions, this is obviously a deal breaker. And there's also a lot of work going on right now. I've, in my experience, find that the most efficient way to account for this is to forget about the distortions, just live with it. And I don't use the so-called anatomical reference data anymore. And in fact, I acquired the anatomical reference data with the same EPI readout. So I have the identical distortions in my anatomical reference and in my functional data. And then, I can obviously not use this for morphometry or something like that, but I have a good like segmentation and then layering for later neuroscientific analyses. And with that, I would like to thank all my colleagues at NIH and overseas, and I thank you for your attention. Are there any questions? Yes.
So when you talk about the idea of sub-millimeter bumps being more the realm of thermal noise than physiological noise, are we basically saying that physiological noise is less of a problem than bumps is a problem?
I repeat the question because I should. Jason Avery asked about whether my slide about comparing physiological and thermal noise means that at high resolutions we are not limited by physiological noise anymore. And my answer is yes. I had a postback, Harry Hull. He looked at like retro-ICOR and physiological noise correction, and it basically didn't matter at all. As soon as you're more limited by thermal noise, your life kind of gets easier in correcting for that because you can't do much about it anyway. In fact, there are a lot of studies out there suggesting that you should never really acquire your data that you are in the physiological noise dominated regime in the first place. If you are physiological noise limited, then turn up your resolution or increase your acceleration and reduce your TR. You should never really acquire data in the physiological noise dominated regime. Yes, we are less limited by physiological noise, which is weird. Yes.
You said something about T2 star blurring, which I wonder if you could just walk through the logic of why you think that it may, you had a conclusion that it might be useful at perhaps neuropathy.
Sure. Sean Merritt asks about the mechanisms of T2 blurring, and maybe I can go back. T2 star blurring, the idea, like let's forget partial Fourier, for example. The idea is that in K-space, the outer K-space lines represent the higher spatial frequencies, and the lower K-space lines represent the smoother spatial frequencies. So if you have if you weight your K-space that the outer K-space lines are kind of underrepresented, the image looks blurrier at the end. And then in EPI and high resolution fMRI, we usually acquire the outer K-space lines and the inner K-space lines like at different time points, so they have different weighting. And this basically works like a low pass or high pass filter in the image space at the end. And what I wanted to say in this slide here is that the way we quantify these, like how bad this high pass and low pass filter is too simple. We should not overinterpret this magnitude point spread function because K-space is complex in the sense that it's like has a real and imaginary part, and basically the higher signal that we have on that side of the K-space can kind of overcompensate the loss of the outer K-space lines that we have back there. When we have a center-out acquisition scheme, this kind of weird Hermite property of K-space cannot be taken as an advantage anymore. Does this answer your question?
But then you went on, when you made a followed up with a proposal about doing partial Fourier.
Right.
That's why.
So in partial Fourier, the way usually in partial Fourier is that you don't acquire the outer K-space lines, but you start like acquiring shortly before you close to the k-space center, meaning that you basically acquire the k-space center first, and then you acquire the outer k-space lines, and the missing parts are then reconstructed with different algorithms like POX or homodyne or zero filling. The default is zero filling, which is the worst case, and with POX you basically iteratively copy the missing data from the other side. And in this case, you still have both of the sides of k-space are reduced compared to the center, because you can only capture the already suppressed outer k-space lines. And it really depends on the algorithm. Yeah. Yes.
How many averages do you need in the high resolution functional MRI?
That's a good question. So I repeat the question. Linkin asked about how many repetitions and averages you need to get a good result. It really depends on your question, your brain area, your resolution at the end, and your effect size. So in the example, I think in this example here, I used 12 minutes. So this was an average of 12 one-minute trials where they always did a finger tapping for 30 seconds and then 30 seconds rest. Similar in, I look it up, in this study where I really only acquired the tiny strip of the motor cortex, and I also had a thicker slice thickness compared to in-plane perpendicular to the cortex, then 12 minutes is doable. If you want to use it more isotropic, for example, we are doing something in visual cortex right now with 0.8 millimeter resolution isotropic, then you need about, I think, 2 averages of 30 minutes each or so. That's also what I do with isotropic digit mapping in the motor cortex. You need a lot of averages. So 2 times 30 minutes, that would be about 900 TRs for, depending on the contrast. So I'm mostly interested in blood volume imaging, as you know. So there you have a lower SNR even with bold image. One big long experiment of 30 minutes might be enough. It really depends on your application. Yeah. Yes. That's not a naive question. It's a good question. So the question was whether in high-resolution layer-dependent fMRI, the superficial layers have a better signal compared to the deeper layers. And it's yes and no. The superficial layers have a stronger signal, but that's actually signal that we don't like. That signal from the big, large draining veins that is not very locally specific. So if you're aiming for a high sensitivity, the superficial layers are the way to go. But if you're aiming for laminar interpretations across cortical depths, then the superficial are more contaminated. And people are talking about correcting like this bias across cortical depths, for example, with vascular models, or using more specific fMRI contrast mechanisms like blood volume that I'm working on to acquire data that are not biased in that way. And I will talk about that a lot Friday next week. Maybe in short, yes, you need to correct for it. You cannot interpret the signal alone in the upper versus the deeper layers with conventional gradient echo bold. Yes. You can use this mic, maybe.
Well, so can you talk about the potential for doing multi-echo scans with 17? Maybe some of the pitfalls that you might have.
Right. So the question is about the applicability of multi-echoes at very high resolutions. It's not straightforward. People have done it though. The problem with multi-echo is that, as I said to Sean's question, we are limited by the readout duration of the EPI. So when we acquire one slice, basically the whole signal is gone already. So because it takes so long to acquire one slice, we usually don't have time to acquire the same slice again with multi-echo because the signal is gone already because it decays so fast. You can do multi-echo, however, in other ways. For example, not using it like for mica denoising, but using it to better characterize the signal, better understanding the contrast mechanisms. People used a flash multi-echo scan where you basically acquire one k-space line a lot of times, then the next k-space lines a lot of times, and then have very, very, very long tasks of 2 minutes or so. And in that case, you can actually have a T2 star fit and then understand the baseline blood volume distributions and the T2 star and S0 changes across cortical depth. But it's not really like practical to do this for application studies. Yeah. It's the time that limits us. Yeah. So you're referring to like a multi-shot segmented EPI. Like after every shot, your echo time starts again from 0, right? You mean like a chittered echo time acquisition?
So like you can use a small feedback when you accidentally one first shot you
Right.
compare the shot echo time, the other like the second one for the longer echo time.
So you're referring to maybe having one EPI acquisition with a different echo time, and then next TR or shortly after that you acquire.
Second excitation for the longer echo.
Right, which would be something like a chittered echo time. So at different TRs, you have different echo times. Yeah. You're not referring to a segmented EPI, right? No. Yeah, of course you could chitter your echo time. Yeah. And then have maybe something like 22 and 32 milliseconds, whereas every one of those images takes about 30 milliseconds to acquire it. And look at that. Sure. Yeah. Yeah. Are there other questions? And thank you very much again.